This is a report on Maria Gaetana Agnesi, who was a very famous mathematician during the very early 17th century. Now, Maria was the oldest daughter of a professor of mathematics at the University of Bologna in Milan. She was born in Milan in 1718 and died in 1799. She lived to be 91 years old. She did most of her work in mathematics from the age of 20 to the age of 40. So let's talk about Maria. Maria was the oldest of 21 children. Again, her father was a professor, so she was given the absolute best tutors, the best teachers. And Maria, at a very, very young age, was shown to have a natural talent for languages. By the time she was 9, she was fluent in 5 languages. By the time she was 13, she was supposed to be fluent in more. Not only that, by the time she was 13, she was translating for other people. Now, at the time that Maria was born, she was her father had married nobility because he had money. His parents were merchants, but his wife was noble, which let him interact with a totally different class of people. And that was one way of bringing yourself up in society, was by marrying into the nobility, and he did. And he not only wanted to show that this was a good thing, he wanted to show that by marrying into the nobility and stuff, that his children were better than other children. So on Sunday afternoons, he would have these little get-togethers where there would be a lot of people from the university and intellectuals from all over that would come to his house. And he would put on little shows, kind of, where his children would perform, only they didn't perform necessarily by singing or dancing or doing any of these things. They did other things. Now, he was a big advocate for education for women, and he wanted to show that his daughter was a case in point where education for women should happen. So what he did was he would have Maria get up, and she would have to recite this stuff, and she would have arguments or debates with different intellectuals there on the merits of education for women. Now, remember, this is the early 18th century, where particularly amongst the nobility, women were expected to be decorative, not functional. They were supposed to look good, bear children, and that was it. Women in particular, at the age of 5, most of the girls were sent off to a convent where they stayed until they were of marriageable age. The education they received in the convent was barely able to read. A lot of times they would have them do some sums, but that was just so that they could keep accounts for their households. And the other thing that they would have them do is everything had to do with taking care of their house and their families. Maria was not exactly the most outgoing person. She was really a very shy and retiring kind of person. And what she really wanted to do was she wanted to go into the convent. Her father wouldn't let her because she was very, very intelligent, and she made him look good. And so she performed at these soirees by arguing with other people, presenting different papers, stuff that her tutors did. Now, her tutors were monks, which were the most learned of that time, and in particular, the one thing that she is always credited for is this long dissertation on education for women that It's very doubtful that she actually wrote it. They think that it was probably written by one of the monks that was one of her tutors. But she was such a good debater that she usually won any discussion and really brought across her point. And since she was a woman and being educated, it really went a long way for the cause. One of the things that happened was when she was 20, her mother died. And she was the oldest of 21 kids. Now think about hiring a housekeeper for 21 kids, somebody to take care of your children. They weren't just real plentiful. And her father, again, wanting to make sure that he had somebody who would make sure that his kids were educated properly, turned over all of that to Maria. Now, she had a lot of younger brothers, and her father being a mathematician, she knew a lot of math and had looked over a lot of different papers from different people that were there. And so she started writing a book. Now, her book is 2 volumes, and it covers all aspects of math. And the important part of this is the reason she was able to write this book was because she was so literate and so good in all the different languages. Now, she was taking papers that were written by people in all sorts of different languages, translating them all into Latin, which was the language of the learned, and so that people now had at least one source that they could go to where everything was put together. She is known a lot for that, and her work is still noted today. You can still look up a lot of stuff if you go to her book. She's the one that brought together a lot of Newton's stuff. She brought on calculus. She was the first one that wrote on calculus, and all of the rest of that. So it was really important. What I'm going to talk about today, though, is something that was important to her, and something that she has been noted for, and that is called the Witch of Agnosy. Now, the Witch of Agnosy is not a person. It's a curve. If you take a look here, it's a curve that's just kind of got a bump in it. Now, the construction of this curve can be very simplistic, but it also can involve a lot of calculus. And later on, people used calculus to construct this curve and to do things like Cauchy-Lorentz distributions. They're all basically this same curve. All right, the first thing we want to do to construct this curve is we need to know what the curve is made of. Basically, what the curve is made of is you have to start with a circle. The circle has a designated radius. It also goes through the origin of the circle, okay? It has a tangent line up here. And this tangent line is going to become very, very important. So here's how you construct the circle. The Witch of Agnosy curve. You start with the circle, and once you have the circle going from the origin, you can draw a line. You're going to draw a line, any line, such that that line is going to intersect the circle and is going to intersect the tangent, okay? From there, you need 2 things. You need to know where it is crossing the circle, and you need where that point is perpendicularly from the x. So here's your x, and here's your y. Okay? You're going to do that multiple times to come up with lots of different points. As you can see, it can be a little tedious. Okay? Each of these, here, here, and here, are points on the curve. Once you have those points, you can then have all the points, and there are some that you can't see here because I've got them in pencil. You can create the Witch of Agnesi curve. But as you can see, I believe that's kind of labor intensive. Now, you can create a chart and go through, do all of this, read it right off the graph. The nice thing about the curve is that you basically only have to do this side, because the other side is the mirror image. It has symmetry, which is really, really nice, because if I know what this side is, all I've got to do is have the exact same point with a negative x, so that you have both sets of points. That makes creating it easier. Well, in the days now that we have calculators. So there's got to be a way that we can do this that's easier, and that we actually have an equation to do this. Well, there is, because if you take a look at this, what you see is that we have a whole bunch of similar triangles that we've created. So we know that we have a ratio and proportion that works with this. Also, we know that we have a circle. So using the equation for the circle and the fact that we have this ratio and proportion, we can come up with an equation for the Witch of Agnesi that will work and will be much less cumbersome than doing all of this. All right, so let's break it down to exactly what we have. What we have is we have a line here, OM, which is the diameter. That is 2 times the radius, A. We have a line here. We have a point here, P, which is the point we want. It's the one we're looking for. All right? If we let P be the point, X, Y, and we have the point here, A, we let the point A be dy. Okay? The X is important. Okay? The X on P, this is how far out we want to go. We don't care about the X on A. So we're going to end up dropping the D here shortly. We're just letting it be there for a placeholder. The Y's are the same. All right? From Pythagorean theorem, well, let's start with ratio and proportion. We know that OM over MN, that's this, over this, is 2A over